When we evaluate a robotic manipulator, we typically look at its physical hardware, the motors, the gearing, the structural alloy. We assume these mechanical components dictate a hard, unyielding limit on what the machine can do, frozen into a static spec sheet. But treating a robot's capabilities as fixed physical boundaries is an obsolete way to engineer a system. Those limits are variables. A modern robot's operational envelope is a dynamic outcome. It is a continuous negotiation between the physical chassis and the software actively compensating for its mechanical shortcomings. We define industrial viability across 4 core metrics: absolute accuracy in positioning, payload capacity under load, the trade-off between speed and precision, and the flexibility of its programming logic. To see how these constraints are actually negotiated, we have to construct a manipulator from first principles. We will map the physical constraints of the hardware, and then layer algorithmic solutions directly over the kinematics to override them. It is this tight coupling of metal and math that defines the actual limits of modern robotics. We start with repeatability, a manipulator's ability to return to the same pose across multiple executions, creating a dense grouping of results. But repeatability doesn't equal accuracy. Absolute accuracy measures how close the physical pose is to the true mathematical coordinate. Baseline kinematic models expect perfectly rigid links and zero-tolerance joints. In reality, micro-imperfections in manufacturing guarantee a physical offset from the mathematical ideal. Correcting this requires a metrology to algorithm pipeline. Engineers use external laser interferometry to measure the physical end effector and quantify the exact pose error. Once mapped, the error is fed into an algorithmic correction tool like the Chaotic Adaptive Sparrow Search algorithm, or CASA. Rather than rebuilding the physical arm, CASA mathematically bends the kinematic model. It adjusts virtual joint lengths and angles until the command perfectly matches physical reality. In tests, this correction reduced maximum positioning error from 3.68 mm down to 0.61 mm. Retaining that sub-millimeter accuracy requires continuous state estimation. The system processes incoming sensor data to verify the physical pose remains aligned with the corrected model. Advanced Kalman filter variants process this data, mathematically accounting for rounding errors in nonlinear dynamic systems, so pose estimates remain stable during continuous operation. Absolute accuracy is an actively maintained algorithmic stake, overriding the physical imperfections of the machine. Payload capacity dictates the mass a manipulator can handle. It is bound by 3 factors: the raw torque of the actuators, the communication bandwidth, and the structural compliance of the arm. When encountering a heavy external load, structural compliance, or physical sagging, is the primary failure point. The arm bends before the motors fail. Soft robotics utilize localized stiffening. When detecting a load threshold, the system alters the arm's material properties, aggressively rigidifying to reduce end effector compliance. By rigidifying only where necessary, the arm supports a heavier payload while preserving the required range of motion for the manipulation task. At extreme millimeter scale limits, the relationship between structural efficiency and payload shifts entirely, moving away from heavy motors toward biohybrid architecture. This chart illustrates the physics of constrained scale platforms. A millimeter-scale necro-robot beetle yields a 6,847% payload ratio. At this microscopic scale, chassis material and structural efficiency completely dominate raw actuator power. Returning to macro scale, conventional industrial arms tackle payloads differently. Rather than changing material stiffness, they rely on mechanical redundancy and algorithmic load mitigation. Arms with redundant degrees of freedom can dynamically reconfigure their posture to absorb and reject heavy external loads without dropping the payload. On systems like the XK3 spherical robot, this mechanical redundancy is paired with a nonlinear disturbance observer and fuzzy PID control. The controller senses payload perturbations and instantly counters them, stabilizing the arm against heavy dynamic forces. Maximum payload limits are dynamic thresholds. They expand outward when engineers manipulate physical stiffness and integrate real-time algorithmic load rejection. High-speed motion and high-precision operation present a zero-sum physical trilemma. They directly compete for the same finite pool of actuator torque and control bandwidth. As velocity increases, momentum pulls against the arm, causing it to wildly deviate from its intended path. Controllers must prioritize tracking fidelity, forcing the physical motion back onto the mathematical trajectory by linking a disturbance estimator directly to a model-based compensation node. The model-based compensation mathematically predicts the dynamic forces that will hit the arm at high speeds. It issues counter-torques to the motors, negating those forces fractions of a second before they cause physical deviations. Other applications reverse this priority. In surgical robotics, throughput and speed are irrelevant compared to absolute reachability and strict positional accuracy. Engineers map the surgical space using preoperative robot capability maps, or RASC maps. These models optimize the base pose and access points entirely for guaranteed millimeter-perfect access, explicitly trading velocity for safety. A robot's speed-to-precision ratio is a deliberate choice hard-coded into its controller architecture, an intentional configuration rather than a mechanical byproduct. Operational flexibility defines how rapidly a robotic system can be repurposed. It measures the friction involved in integrating the hardware into shifting task workflows. True workflow flexibility first requires task decomposition. Complex procedures are broken down into isolated action primitives, known as thurbligs, translating manual tasks into modular robotic commands. Executing these modular commands is moving away from rigid, hard-coded logic and toward human-centered programming interfaces designed for non-experts. Frameworks like PROgrammar utilize augmented reality for behavioral authoring. Users map workshop tools directly to the robot's perception, seeing spatial constraints projected in real time. Paired with trigger action programming, a factory worker can rapidly modify robot operations, authoring complex reactive behaviors without writing a single line of code. Learning-based approaches can accelerate this even further. Transfer learning pipelines and expert-guided policies allow a machine to acquire new behaviors far faster than manual programming allows. But software flexibility also carries a vulnerability. When programming approaches are tied to specific, aging hardware platforms, the comparability across studies destabilizes, degrading community replicability. Operational flexibility relies on modular software logic and accessible human interfaces. These digital frameworks dictate the machine's utility far more than its mechanical tool changers. We have mapped the modern robotic manipulator from the ground up, layering algorithms over kinematics to create a unified platform. Absolute accuracy is actively sustained by state estimating Kalman filters and real-time kinematic correction through CASA. Payload limits are amplified through localized physical stiffening and nonlinear disturbance observers. The trade-off between speed and precision is tightly governed by predictive, model-based compensation, and operational flexibility is unlocked by augmented reality programming interfaces and rapid transfer learning. Evaluating robotic performance through the lens of a static hardware spec sheet is obsolete. Hardware provides the baseline, but the system's true capabilities are written in the software. To engineer or integrate modern industrial robotics is to master this continuous, negotiated loop between physical mechanics and algorithmic control.